Hello, I Anand Jain from Hanumangarh, Rajasthan welcomes you to Sridevi Classes YouTube channel where we inculcate interest and confidence in science and engineering subjects. Today in our class 12th physics playlist, in our chapter electromagnetism, we'll study Ampere Circuital law and understand how the line integral of magnetic field get connected with its source current, and in symmetrical current distribution and symmetrical magnetic field conditions, how easily we can correlate source current with produced magnetic field. And we'll also learn magnetic field of a solid cylindrical current carrying conductor having uniform current density, and we'll study both internal and external magnetic field for this cylindrical conductor. So let's start. Like Biot-Savart law, Ampere Circuital law is an alternative approach, and a quite convenient way to analyze magnetic field. Ampere Circuital law consider a surface enclosed by a line boundary loop, and it connect magnetic field on boundary line and total current passing through that surface area or enclosed by the loop boundary. This Ampere Circuital law is applicable to both symmetrical and unsymmetrical current distribution. But if current distribution produce a symmetrical magnetic field around it, then it will make calculation quite convenient and simple. Ampere Circuital law states that closed line integral of magnetic field flux density around this closed boundary loop is equal to mu0 times the summation of current which is passing across this surface area which is enclosed by the boundary loop. This left side of Ampere Circuital law, closed line integral of magnetic field flux density, is also known as circulation of magnetic field. As we know, magnetic flux density is amount of force on unit north pole, and force multiplied by this elemental displacement is small elemental work done in moving a unit north pole on this boundary loop for small displacement, and this is total work done in moving a unit north pole all around this closed loop, and this is known as circulation of magnetic field. And as per Ampere Circuital law, this total amount of work done in moving a unit north pole around closed boundary loop or closed line integral of magnetic flux density is mu0 times the summation of total current which is enclosed by this boundary and crossing or passing through the area enclosed by the boundary. Now, with the use of this Ampere Circuital law, we will find out magnetic field flux densities with great ease and convenience when current produce a symmetrical magnetic field around it. Now, let's first prove or verify Ampere Circuital law, and let's consider a straight infinite long current carrying conductor carrying I current. Now, due to symmetry of this current as per Oersted observation and Maxwell right-hand rule, it will produce magnetic field in the form of concentric circle around it. Let's consider a closed circular path of radius r around this conductor with this conductor as central axis for that path, and let magnetic field flux density on this boundary loop is b Tesla. From Biot-Savart law and mathematical analysis, we have found that for a long straight I current carrying conductor at mid positions at perpendicular distance r, the magnetic field flux density is given as mu0 I upon 2 pi r, and for this circular loop boundary which we have considered, everywhere the distance from source current is r, so the magnitude of magnetic field flux density over this loop remains the same, and due to symmetry of current distribution, everywhere on this circular path magnetic field is tangential as given by Maxwell right-hand rule. Thumb is pointing the direction of current and curl of finger indicate this magnetic field in the form of circular loop. So the closed line integral of this magnetic field flux density can be obtained when we consider a small elemental length. Then for this elemental displacement dl on assumed circular loop, dot product of b and displacement is b dot dl, and total line integral of magnetic field flux density around this closed loop can be obtained by closed integration of b on this loop length everywhere due to symmetry of magnetic field which exists around this current, magnetic field tangential to this circular loop and displacement on this circular loop both are in the same direction. So angle between B and displacement becomes 0, cos 0 becomes 1. And since everywhere the magnitude of magnetic field flux density is also constant, so this B will also come out of integration as mu 0 I upon 2 pi r, and this simply become integration of circular loop. So closed line integral of magnetic field flux density is mu 0 I upon 2 pi r multiplied by integration of length for circumference length 2 pi r, and integration of dl is L, limit is from 0 to 2 pi r, and when we substitute limit, this 2 pi r get cancelled by this denominator 2 pi r, and closed line integral of magnetic field flux density comes as mu 0 times the current enclosed in this loop or passing the surface area enclosed by the loop, and this is Ampere Circuital law. In place of this symmetrical circular loop around conductor, Ampere Circuital law, closed line integration of magnetic field flux density equal to mu 0 times enclosed current, can also be proved for unsymmetrical observation positions. Let's consider another closed but irregular path as shown here, enclosing current I, and consider a small elemental length dl on this boundary path, and let's find out closed line integration of magnetic field flux density around this irregular closed path. Now here magnetic field flux density by conductor current is tangential to this radial line, and dl displacement on boundary makes a angle theta with magnetic field flux density. So this dot product of B and elemental displacement become B dl cos theta, and magnetic field flux density at a r perpendicular distance from straight long conductor carrying I current at mid position is given as mu 0 I upon 2 pi r. So in place of B magnitude we can substitute mu 0 I upon 2 pi r, and this dl cos theta is component of dl along B direction or along tangential direction, and let's call that displacement shown by blue line as ds. So ds is perpendicular arc distance on circular periphery at this observation position. In this integration, mu 0 I divided by 2 pi is a constant which can be brought out of integration, and this become close integration of ratio of arc length ds and radius of observation position from current source r, and this arc by radius is small angle subtended by this arc length at this source current position. Let this angle is d theta. So this is closed integration of d theta angle by this irregular boundary considered by us, and any closed boundary produce a limit of 0 to 2 pi in one enclosure around this position. So this is integration of elemental angle in limit 0 to 2 pi. Integration of elemental angle is angle, and when we take limit 2 pi and 0, this become 2 pi, get cancelled by 2 pi, and our results will become closed line integral of magnetic field flux density is mu 0 times unclosed current, and it doesn't depend upon symmetrical position of current in reference to boundary at which we are doing closed line integral. The only consideration is that this current should be unclosed by that boundary, but we will soon find that if current position is symmetrical and magnetic field around it got symmetry, then this Ampere Circuital law makes our magnetic field analysis quite convenient. In the Ampere Circuital law, closed line integration of magnetic field flux density is equal to mu 0 times algebraic summation of total current enclosed in boundary over which this line integration is done. And when we do algebraic summation of current, it means current is taken both positive as well as negative as per convention of right hand. And if we make an anti-clockwise movement on this closed loop, then as per right hand rule, when finger are curled along movement on loop anti-clockwise, the upward thumb indicate positive direction of current. So in this example, current I and I1 is positive and I2 is negative. So this algebraic summation of enclosed current will become I plus I1 minus I2, and only those current should be considered which are enclosed. Any current which is outside this boundary will not be considered in this algebraic summation of current. In one really difficult problem, examiner can change orientation of loop as shown here. When we make closed line integration of magnetic field flux density over this loop as shown here as per our right hand rule and convention. For this clockwise travel, this enclosed current I2 is positive and this I3 is negative, and for this anti-clockwise travel, this I1 become positive, and in this loop all three current I1, I2, I3 are enclosed, but I1, I2 got positive sense and I3 got negative sense. So algebraic summation of current will become I1 plus I2 minus I3. In Ampere Circuital law, this algebraic summation of current is that current which is enclosed by the boundary or passing across this surface area enclosed by the closed path of line integration, and in this case this current is outside this closed boundary. So closed line integral of magnetic field flux density over this path will become 0, and this can be explained as on some part of this closed loop line integral of magnetic field is positive and to some part it is negative, and total summation for this entire path becomes 0 as there is no enclosed current in this path. So we have seen that Ampere Circuital law interconnect magnetic field with source current, and if current distribution is symmetrical and at steady positions the magnetic field produced by current got certain symmetry, then our calculations become quite convenient and easy, and such example can be a long straight conductor or a solenoid or toroid. One should also appreciate that Ampere law is quite equivalent to Gauss law of electrostatics, and both produce easy evaluation of field. In application approach, Ampere law in magnetic field and Gauss law in electrostatics are quite identical, and both help us in easy evaluation and determination of field values. Ampere Circuital law and Gauss law establish a great similarity between electric field and magnetic field. Ampere law relate magnetic field flux density on boundary of this closed line path with enclosed source current, and Gauss law relate electric field intensity on this boundary of closed surface with total amount of charge enclosed in that closed boundary. So both Ampere Circuital law and Gauss law in their respective field positions are quite identical in application approach, but as a caution we also note that Ampere Circuital law is applicable only to steady current conditions and it is not applicable to time varying or transient current conditions. In symmetrical current distribution, when magnetic field produced is uniform and symmetrical, it can be easily obtained by Ampere Circuital law. Let's find out magnetic field of a straight current carrying infinite long wire length. We have given a long straight conductor wire carrying I current along its length. Now due to symmetry at a circular periphery of constant radius, magnetic field magnitude is everywhere the same and magnetic field is also tangential on this periphery. Let's consider a circular path of radius r around this current carrying conductor with current axial position and center of this circle get coincide. Consider an elemental length dl on this path and obtain closed line integration of magnetic field flux density around this closed loop, and as per Ampere Circuital law it is equal to mu0 times summation of all enclosed current, and only this I current is enclosed, and as per our right hand convention this current for this anti-clockwise travel upward in direction become positive. Magnetic field around a long straight current carrying conductor got a cylindrical symmetry. It means the field magnitude everywhere on this circular path of radius r is constant and is also tangential to the circumference of this circle, and this symmetry will simplify our calculations, as in this closed line integral of magnetic field flux density, the angle between magnetic field flux density and elemental displacement on this circular path both are tangential to this circular arc, and for cos 0 equal to 1, and everywhere on this circular path this magnetic field flux density being constant come out of integration, and this become mere closed integration of entire circular path, and for one circular path the limit of length becomes 0 to 2 pi r. As per Ampere Circuital law, it is equal to mu0 times the only current enclosed in this path I. Now the left hand side integration of dl become L, and with limit 0 to 2 pi r it become 2 pi r. So B multiplied by 2 pi r is equal to mu0 I, or magnetic field flux density on this circular path B can be written as mu 0 I divided by 2 pi r, and this relation clearly indicate that magnetic field flux density is directly proportional to source current magnitude, and if the source current become 6 times, the magnetic field flux density also becomes 6 times. And the same relation also tells us that magnetic field flux density is inverse of radial distance from straight conductor, and this inverse relationship clearly indicate that if we double the distance from central axis of observation position, the magnetic field flux density will become half, as indicated by this inverse hyperbolic relation of magnetic field flux density and perpendicular distance from conductor. From this Ampere Circuital law, using symmetry of current and magnetic field distribution, we have obtained magnetic field flux density at a r distance from a straight long I current carrying wire as mu 0 I upon 2 pi r, and the same result we have also obtained from Biot-Savart law, which relate elemental magnetic flux density contribution to its source elemental current length with position vector r by this relation, and after a rigorous mathematical process we have obtained the same result as we have obtained easily from Ampere Circuital law using the symmetry of magnetic field distribution here in this case. So both Ampere Circuital law and Biot-Savart law relate the source current with magnetic field in their own manner, but both finally attain the similar type of result, but definitely by an independent manner. The magnetic field produced by a long straight current got a cylindrical symmetry, and this fact can be used in Ampere Circuital law to find out magnetic field of a solid cylindrical conductor. And let's consider a long straight cylindrical conductor of cross section radius capital R, which carries a steady I current, and this current is flowing in this wire with uniform current density all across its cross section. Now the magnetic field produced by this cylindrical current is in the form of concentric circles around this central axis of cylindrical current carrying conductor, both for internal observation position and external observation positions. We have to find out the magnitude and direction of magnetic field flux density at a distance r, which is internal and less than conductor radius, or an external point of axial distance small r greater than radius of cylindrical conductor. So we have to find out magnetic field for internal as well as external positions. To find out magnetic field flux density at an external position by Ampere Circuital law, consider a coaxial circular path of radius r, which is greater than radius of this cylindrical conductor around this current carrying cylindrical conductor as shown in this figure. And due to symmetry of current and magnetic field, the magnetic field become tangential to the circumference of this circular path. Now to apply Ampere Circuital law, the closed line integral of magnetic field flux density is carried out, and as per Ampere law it is equal to mu 0 times summation of current, and the entire I current is enclosed by this Ampere closed loop. So this become mu 0 times I, where I is current of cylindrical conductor. The magnetic field produced by this long straight cylindrical current carrying conductor around it at outside position got a cylindrical symmetry. That means magnetic field flux density everywhere on this circular path got the same uniform magnitude, and magnetic field flux density is tangential to circumference of this cylindrical path. So the closed line integral of magnetic field flux density, which involve dot product of magnetic flux density vector and displacement vector, become b dl cos 0, as both displacement on circular path and magnetic field flux density at that position become collinear, and angle between the two becomes 0 and cos 0 become 1. Since everywhere b and dl are in the same direction and the magnitude of b is the same, so being constant, this b will come out of integration and this become mere integration of circular path length, and this closed integral become integration with limit 0 to 2 pi r, where 2 pi r is peripheral length of this circular path. And as per Ampere Circuital law, the closed line integral of magnetic flux density around this circular path is equal to mu 0 times the total current enclosed in this path, that is conductor current I. Now integration of dl become L, and with limit 0 to 2 pi r it become b multiplied by 2 pi r, and this is equal to mu 0 times enclosed current I, and simplification fetch the result B is equal to mu 0 I upon 2 pi r, and this expression is same as this cylindrical current is concentrated as central axial wire position. So for all external positions, a cylindrical conductor and a line conductor produce identical amount of magnetic field for same amount of current and same radial distance. So this magnetic field is directly proportional to current in conductor. If conductor current is doubled, the magnetic flux density also get doubled for the same position, and this magnetic flux density is inverse of the radial distance. Double distance position will have half value of magnetic flux density. So B and distance of observation position from central axis got a hyperbolic variation. Now to find out magnetic field flux density to some internal position, consider another closed circular loop of radius r, and this r is less than radius of this cylindrical conductor. Let magnetic field flux density on this circular loop inside this cylindrical solid conductor of uniform current density is B dash. So as per Ampere Circuital law, the closed line integral of magnetic field flux density is mu 0 times algebraic summation of enclosed current, and for this circular path, the enclosed current is not the entire total current of conductor. The current got uniform current density per unit cross section. So for r radius cross section area pi r square, the current I got a density I upon pi r square, and for this circular cross section area of pi small r square, the enclosed current I dash will become total current radius of internal circular loop small r divided by r square, and this capital R is radius of cylindrical conductor. So in this expression we can substitute I dash as I upon r square by capital R square, and this line integral due to cylindrical symmetry of magnetic field flux density B dash and peripheral length got alignment, and angle between two is 0 degree. So cos 0 degree become 1, and all around this circular path internal magnetic flux density is constant. So that constant come out of integration, and this become mere integration of the circular length, and this is equal to mu 0 times enclosed current in this circular path, and that is total current multiplied by square of the radius of inner circular path divided by square of the radius of cylindrical conductor. So here, due to cylindrical symmetry of magnetic field flux density, the closed line integral of magnetic flux density will become magnitude of magnetic field flux density multiplied by integration of circular path length, and it is equal to mu 0 times enclosed current in this circular path. And if total current of cylindrical conductor is I, then for r radius of cylindrical conductor in this circular path of small r radius, enclosed current is I small r square upon capital R square. Now this integration of the circular length become 2 pi r, and simplification of left hand side and right hand side, remove 1 r from both sides and 2 pi to the other side, will make internal magnetic field flux density as mu 0 I multiplied by r divided by 2 pi r square. And this expression clearly indicate that internal magnetic field flux density is directly proportional to the distance of observation position from central axis, and there is a linear variation at the central axis. For r equal to 0, magnetic flux density is 0, and as we move away from this conductor, the length of closed path increases in a linear portion, but enclosed current increases in a square of the radial distance relation. So ultimately our magnetic field flux density increases in a direct proportional to radial distance for all internal positions. Now for simplicity of mathematical calculation, we can consider this internal position distance from central axis as x times of radius of cylindrical conductor, and when this small r is replaced by x times capital R, 1 r will cancel out, and this expression become x times mu 0 I upon 2 pi r, and this mu 0 I upon 2 pi r is the maximum amount of magnetic field flux density produced by this conductor at its surface, and at x times radius distance position, the magnetic field will become x times the surface value. So for half of radius position, magnetic field will become half of surface value. This figure in blue frame represent variation of magnetic field flux density of a current carrying long straight cylindrical conductor for both internal positions and external positions. For internal positions, magnetic field flux density is directly proportional to distance from central axis, and this is a linear variation. And for external positions, magnetic field flux density is inverse of the distance from central axis, and thus become a hyperbolic variation. And magnetic field flux density attain its maximum value at surface of this conductor, and that is mu 0 I upon 2 pi capital R. And at this central axis position for R equal to 0, there is no magnetic field flux density, and it increases first linearly inside the cylindrical conductor, attain maximum value at surface, and then it decreases in a inverse of distance from central axis as shown by this hyperbolic relation. It means for both half of radius distance r by 2 and at 2r distance from central axis, the magnetic field flux density is half of surface value. We hope this useful and informative learning video has taught you each and every aspect of Ampere Circuital law, and now you can understand the similarity between Gauss law and Ampere Circuital law, and how easily we can find out magnetic field flux density of long straight cylindrical conductor to both internal position and external position by use of cylindrical symmetry of magnetic field produced by such current distribution. Our other learning video are equally useful, and you can use them in your studies and share them with your friends. And if you need our online doubt clearing classes and exam centric study notes, do join our membership by clicking join button just beneath. Happy learning. Thank you very much.